Hello everyone, welcome to the course Material Characterization by Professor S. Shankaran from IIT Madras. This is the live problem solving session for the week 9 of the course. I am Mayank Goyal. I am a research coordinator Department of Electrical Engineering IIT Bombay. And the details of the course are the course is being taught by Professor S. Shankaran, who is an associate professor at the Department of Metallurgical and Materials Engineering IIT Madras. The course plan for this week is week 9 is quantitative analysis and residual stress analysis in XRD and instrumentation details and demo experiments of XRD. This session is happening every Sunday 6 p.m. to 8 p.m. at this Google Meet link. So I will first try to cover the topics for this week using some AI generated slides. So first we will see how XRD is used to diagnose crystalline size and microstrain. So first we look into periodicity. So as assume you have a if you have a monoatomic gas, so a gas has no structural periodicity and it is the atoms are completely randomly distributed. So there will be no diffraction at all, or any diffraction will be completely random. So all the so you will not see any features in your XRD curve, and all you will see is a completely horizontal line. Now, in case you have an amorphous solid or liquid, then since they are amorphous, so they also don't have any 3D periodicity or any order in the sense, but there are some, but there is some order in their lattice. So some particular interatomic distances might have some statistical preference because they are more compared to other. So what you will see is some background with some very broad peaks, random, which have no correlation to the phase of the material. And if you have a crystalline solid, then they are arranged in a proper 3D lattice, and they will have sharp intensity peaks, which are governed by Bragg's law. So which can be used to uh, understand the crystal lattice. And so why crystalline peaks are sharp? So at exact Bragg angle, all the deflected scattered X-ray waves are perfectly aligned in phase, so they all constructively interfere, and which gives you the high intensity peak. And as soon as you move away from the Bragg angle, the 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 scattered waves become out of phase, and ultimately when you combine a lot of them, they all become they the combination of all the scattered waves results in destructive interference, so you get only flat line. So only at the Bragg's angle you are able to get sharp peak. So that only you are able to get constructive interference. That is why you get very sharp peak. This is for highly crystalline materials and with large size. Now the and when let's zoom into a single peak. So so in a single peak you will have multiple things. So one will for the main thing that you will see is your I peak, which is the intensity at the peak of at the maximum intensity in your peak. And then you will have something called I background. which is the intensity in the flat region. So this could be coming from your substrate, or from your instrument, or it could be noise. So so this is the background, and then you will have something called integrated intensity, which will be the integrated intensity, which will be integrated area under the curve, which is what you use for for your calculations, and not just I peak. Then you take IFWHM will be which is intensity at half maxima. So how you calculate your half maxima is you take your peak intensity and subtract your background intensity, and then divide by 2. So the value that you get, that is your half maxima. So you take the intensity of half maxima, and then you calculate the full width of the peak of your peak at half maxima, which is this length. So this is called full width at half maxima, or FWHM. Now you, as you see your the peak here has some shape to it. Now now this shape can be fitted with three different functions. One is your Gaussian, one is your Lorentzian, and one is your pseudo void, which is a linear combination of your Gaussian and Lorentzian functions. So Gaussian function is calculated at certain angle, at certain 2 theta angle ith point on the peak. I 2 theta I is, that is equals to IP into 4 into ln log of 2 of square root divided by square root of pi into your width of FWHM, into exponential of minus. You take the theta I angle for which you are calculating the intensity, minus 2 times your theta p, which is the angle at which you got your maximum intensity, square divided by w square. So this is nothing. So it's WFWHM square. So this whole thing is just one thing. Then you go for Lorentzian. It's a much simpler equation. Peak intensity into 2 by pi FWHM width plus divided by, so it's minus 1. So it's everything inside is divided. 1 plus 2 into theta I minus 2 into theta p square divided by w square. So so these are two different functions which can be fitted on a curve. Then you have your void function, which is a combination of your Lorentzian and your Gaussian curves. So the actual void function is much more complicated. So instead of that, we use pseudo void function, which is given here, which is just a linear combination of your Lorentzian and Gaussian function. So it's just eta L plus 1 minus eta G, where eta is your mixing fractions from 0 to 1. So, so doing anything for calculating for calculating any quantitative function, you have to first model the peak. So it is a modeling the peak is the prerequisite for quantifying and separating instrumental size and strain effects. So deconstructing experimental broadening. So this is the final broadened curve that you get, and it is mainly composed of three variants, three consequent constituents. One is your b one is your b size, which is broadening coming from a crystallized size. So it is broadening due to finite crystal volume. Next is your b strain, which is broadening coming due to lattice distortion and accumulated structural stress. And the third will be your b instrument, which is coming from which is the broadening caused by the diffractometer's internal optics and geometry. So there are optics inside a diffractometer which will create broadening in your signal. Then the geometry and the detectors, they will also result in some broadening. So V experiment is the experimentally measured FWHM. So that is the FWHM you will measure in your final output. But to find the material's true characteristics, we must first strip away instrumental noise and then separate size from strain. So how you can do that? So to correct instrumental correction workflow, you first isolate the baseline. So you prepare a well annealed large grain sample of the exact same material that you are trying to quantify. So if it's very well annealed, then it will relieve all strain. So you will not get any strain based broadening. And if you take very large grains, then it will also eliminate size broadening. So all that you will be left with is your instrumental broadening. So now you take the diffraction pattern, and the experimental conditions should be exactly same as your main sample. All your all the temperature, the angles, the step size, step time, everything should be same as your main sample and your calibration sample. And so now whatever your the peak width you will get is only your instrumental contribution, because we have removed the size broadening and strain broadening. Now now to get just now to get broadening from your sample, you can just subtract the your FWHM you got from your sample minus the FWHM you got from a calibration sample. So you can calculate W square sample equals to W square FWHM minus W square instrument. So now your W square sample does not contain your instrumental noise. It only contains values from your size and strain. So now so the addition of broadening from all three components is different if you're considering Lorentzian peak or if you're considering Gaussian peak. So in Lorentzian peak, the you add linearly. So B experiment equals to B size plus B strain plus B instrument. For Gaussian peak, you add the squares. You take the sum of squares. So B experiment square equals to B size square plus B strain square plus B instrument square. Now isolating variable one, that is crystallite size. So if you take your Scherer equation and you make cos theta to bring cos theta left, so it becomes B cos theta equals to 0.9 lambda by T. So now if you see that, so B cos theta you can calculate experimentally. So you know your broadening and your Bragg angle at which you have got that particular peak, and your right hand side is completely from your material. So left hand side is completely from your experiment data. So that you can calculate for each peak your B and cos theta. And on right hand side lambda you know, T is something you don't know. But let's say if let's say size was the only contributor to broadening, that means T will be the same. So the T is same for every peak, and you don't have any other broadening effect, only your size broadening is there. Then this particular term will be constant. So the value of B cos theta should remain constant across all peaks. So if you calculate B cos theta for all peaks, and if it is the same, that you would know that size is the only contributor to broadening, and then you can use this formula to get your T, and that will be your correct answer. But if you have microstrain also involved, then you will have then your B cos theta will be equal to minus 2 delta d by d sine theta, where your delta d is your strain accumulated in the lattice. So now you can see here, now your b cos theta is inherently dependent on sine theta also. So theta is so one theta function is dependent on other theta function. So this you cannot just randomly separate out, and it will be so here b cos theta value will be different for every peak because the theta value is different for every peak. So sine theta is different for every peak. So b cos theta will be different for every peak. So you will not get constant value if you have both strain and your size involved, or just strain involved. So what you can do is you can create a plot called the Williamson Hall plot. That is, you plot your b cos theta versus your sine theta. So at each peak, for each peak you calculate your b cos theta as well as sine theta, and you plot that. So when you plot that, your you can see see so your b cos theta will be sum of your size component and your strain component. So so since your size component does not depend on sine theta, that will just be a constant, and your and your strain value will be will come into their slope. So so it should give you a line y equals to mx plus c, where y is your b cos theta, x is your sine theta, m is your slope which gives out the strain value, c is your y intercept which gives out your size value, size component. So by plotting b cos theta against theta sine theta, we force isolated physics equations into a single linear geometry. So now, so this allows us to read size and strain directly off the graph. But if you see, we just added the two components. We linearly added. We didn't square or anything. So this implicitly assumes that peak shapes are Lorentzian. So we are assuming that these are Lorentzian peaks. That is why we have just added the peaks, added the components. So now, if you get a straight horizontal line, if your b cos theta is a constant for all the p's, that means that the only significant contribution is coming from your size and not your strain. But if you have a slope in the line, that means if b cos theta is a linear function of sine theta, then straight bonding is also important, and it is also actively contributing to your material state. So, so if we, so if you take ball milled powder, so ball milled forces powders to become finer, and simultaneously they accumulate heavy microstrain, which is evidenced by the steep linear slope as you can see here. But when you anneal them at 13-15 degrees Celsius for 2 hours, all the strain is completely relieved, and this is indicated by the zero slope here. So what are the applications of XRD? So it can be used for crystal sector determination. So this is the main fundamental use case of XRD to identify atomic arrangements. It can be used for residual stress measurement. So it can be used to calculate the residual stress inside your material. So which is very important for evaluating the structural integrity of engineered components. Then it can be used for phase identification. So it can be used for isolating and identifying distinct phases within a mixed substance compound. So if you have a compound with where you have mixed two or three phases of the same material or different material, then looking into the peaks, you can calculate your this the composition. Then you can do it for texture analysis. Look, it is to determine the precise crystal origin between a broader macrostructure. So you can see your XRD at different areas on your large sample, and by look and looking into your XRD peaks, you can get the crystal orientations at different areas. So that will give you texture of their material. So an XRD typically gives you two things. One is the peak position and one is a peak intensity. So peak position is used for geometry and indexing. So it is used for determining your crystal structure, and peak intensity is used for determining your phase mix. Is used for phase mixture and quantity. So it is used for phase identification and quantitative analysis. You know the formula, Bragg's law, lambda equals to 2d sine theta. So and for cubic the d equals to a by under root h square plus k square plus l square. So you can put this here, and it will, so you can get sine square theta divided by h square plus k square plus l square, which is sine square theta by s, which is equal to lambda square by 4a square. So here you can see your sine square theta is is equal to s into lambda square by 4 square. So you just have to so your HKL are all always integer. So your s equal s h square plus k square plus l square will also be an integer, and your lambda square by 4 square will be constant for any given pattern. So if you find s, you will get the whole crystal structure. This is for cubic lattices. And then you will have the selection rules for HKL, H square for S, that is selection rules for S, H square plus K square plus L square. So if for simple cubic, it can be 1, 2, 3, 4, 5, 6, 8, 9, 10. For BCC, it will be 2, 4, 6, 8, 10, 12, 14. For FCC, 3, 4, 8, 11, 12, 16. For diamond cubic, it will be 3, 8, 11, 16. Now, some integers are impossible. They cannot, that are 7, 15, 23, 28, 31. So no combination of h square plus k square plus l square will ever sum to these numbers. So you don't have to even consider them for it during your indexing. So till now we were talking about cubic structures. Now let's say, but there, if you know, there are 14 different Bravais lattices, and cubic is just one. Cubic is just I think 3 or 4 of them are cubic. So now if we consider tetragonal lattices, then it your sine square theta becomes a proportion, becomes dependent on two variables, a and c. So your a is your lambda. So your tetragon. So your cubic system relies only on cubic systems only have one variable, that is your a. So lattice, it only has one lattice constant a, but tetragonal systems have two lattice constant a and c. So it becomes dependent on two lattice parameters, capital A, that is lambda square by 4a square, and capital C, that is lambda square by 4c square. So your sine square theta becomes dependent on these two values, a into h square plus k square plus c into l square. So now now you have, for getting your a, to calculate your a and c, you have to use two-step algorithm. One is first you isolate A, so it first only take the lines where L is 0. So you only take so only where L is 0, you take those lines. So now your sine square theta becomes A h square plus k square. Since L is 0, so C h square terms go away. Now A is h square. Now the permissible values for h square plus k square can only be 1, 2, 4, 5, 8. So your A will exactly be 1, 1 half, 1 4, 1 5, or 1 8, etc. times your sine square theta value for these particular lines. Now, now you consider the lines where L is not 0. Then you have sine square theta equals to, then you have sine square theta minus A h square plus k square equals to C L square. So now you know the values for A h square plus k square. You put that here to get your value of C. So now, now using this this relation 1 by 4 1 by 1 half 1 by 4 1 by 5 1 by 8, if you put that here you will see that CL square will have ratios of 1 4 9 16, because L it has L square, so L can be 1 2 3 4 5 6. So you have cubic structure, you have tetragonal structure, you have hexagonal structure. So the governing equation for cubics is your sine square theta equals to S into lambda square 4r square. So it has only one constant S. So the permissible rule are determined by the lattice type, which is simple BCC FCC. For tetragonal, you have sine square theta equals to A h square plus k square plus C L square. So now you have two constant A and C. For hexagonal, the governing equation becomes sine square theta equals to A h square plus hk plus k square plus C L square. So it has two constants. It has also two constants A and C, but here A is lambda square by 3a square and not 4a square. So now we move to phase identification. So we from geometrical mapping we are moving to quantitative analysis. So the intensity problem. So the core premise is that relationship between X-ray intensity and phase concentration is not linear, and the culprit for that is mass absorption coefficient. So the intensity depends heavily on the mass absorption coefficient of the entire mixture, and because mass absorption coefficient itself changes as a function of the mixture's concentration, the signal is dynamically dampened. So we must mathematically untangle the phase from its surroundings. So we have to separate out the phase intensity from the mass absorption coefficient. So for pure substance, you will have for pure substance the intensity is as is a function of multiple values. Your original or intensity of our original radiation, your lambda, your so it has a lot of terms, as you can see here. So from when you we come to when you come to mixed a substance, we come we talk about intensity in relative terms. So we take I alpha equals to k1 c alpha by mu m. So k1 is your unknown constant because we don't know because incident beam intensity is generally unknown. C alpha is your volume fraction. So intensity is multiplied by C alpha because the diffracting volume is physically less in a mixture. So it's lesser than pure. So we are doing C we are multiplying with volume fraction and then divided by mu m, which is a mass absorption coefficient of the mixture. That gives out your intensity of that particular phase. So there are three methodologies for phase identification. So because the incident intensity is unknown, we cannot measure absolute intensity. We must use intensity ratios against a standard reference line. So one is external standard method, where you use a you take a when you take a pure you take another sample which is pure phase, and you measure the XRD for that, and you take a reference line from that to measure your measure the phase fraction in your particular mixed sample. Or you can take direct comparison method, where you take reference line from another space that is already present in the mixture. So you compare two different phases within the mixture. Another is your internal standard method, where you add a predetermined amount of a non-foreign material. So you take another material which is not present in your material, and you take a known amount and you mix it into your material physically, and then it acts as a baseline reference. So assume a two-phase mixture of gamma and alpha. So your I gamma would be K2 R lambda R gamma C gamma by 2 mu m, and I alpha will be equal to K2 R alpha C alpha by 2 mu m. And if you divide them, it will becomes I gamma by I alpha equals to R gamma C gamma by R alpha C alpha. So your so your mass absorption coefficient and your constant K both disappeared on dividing, because they are common for both phases. But we here have a new term called R. So R gamma and R alpha are purely substance dependent constants, which are calculated from known crystal structures and lattice constants. So they are predetermined for a particular phase or material. So it solves the mixture. So you obtain your I gamma by I alpha directly from a diffractogram pattern, and R gamma and R alpha you will get from your standard data, standard structure data. You can get your R alpha and R gamma. Then from this, then you can calculate the volume fraction C gamma by C alpha, and you know if there are only two phases, then C alpha plus C gamma will be equals to 1. So from raw X-ray diffractogram, you can take your peak position and peak intensity. From peak position, you calculate your S, A, C, etc. And you filter it via selection rules. So and then you can calculate your crystal geometry from I from peak intensity. You can get from peak intensity, and from theta you can, once you have a structured data, you can calculate your R by comparing it with your standard values, and then you compare your intensities, and then that way you can quantify your phase volume fractions, and this gives us your complete material identity. So a single diffraction scan acts as a master key. So by analyzing the pattern, position, and intensity, we can reverse engineer the complete physical state of the material. So from the type of diffraction pattern, we can calculate the crystal structure. From the angular positions of the lines, we can get the shape and size of the unit cell. And from integrated line intensities, we can get the atomic arrangement within the unit within the lattice. That is your phase and orientation. So first is your crystal structure. So the most reliable method for determining an unknown crystal structure relies on measuring the sine squared theta values. For cubic systems, we can distill the two fundamental physical laws in a single diagnostic constant. So, so because lambda square by 4a square is constant for any pattern, the sum of integers must yield a constant quotient when divided into the absorbed sine squared theta. So this will reveal the crystal size. So if you have a cubic lattice, your sine squared theta by h square plus k square by l square should be constant. And the permissible s value h square plus k square l square for different cubic structures will be can also be known. Now if you have tetragonal system, you have sine square theta equals to a h square plus k square plus c l square. So one a is calculated from hk 0 lines, and cl is calculated then from other lines. One a is known. Next is your phase identification. So in real world materials like steel, they are rarely single phase. They are complex mixtures such as austenite and martensite. So X-ray diffraction allows us to identify and quantify the exact concentration of a specific phase within the material, within a mixture. So to calculate the concentration of unknown phase, we bypass the complexities of absorption coefficients by taking ratio of intensities. And for that, we need for that the most widely used approach is the direct comparison method, where we compare the compare one line of from one phase to line of another phase in the same mixture. In external standard, we compare it with a line from a pure pure phase sample. In internal standard, we mix a foreign sample into the specimen, and we compare it to the line from that sample. So so in direct comparison, you get the formula I gamma by I alpha equals to R gamma by R gamma C alpha gamma divided by R alpha C alpha. So R gamma R alpha are are derived from crystals, known crystal structures, and in two-phase system, C gamma plus C alpha equals to 1. So we can once we calculate the ratio, we can immediately get the exact phase concentration. Next, we come to residual stress. So industrial engineering relies heavily on understanding the residual stress within a component, and X-ray diffraction acts as an atomic level strain gauge. It calculates macro engineering stress by observing micro lattice distortions. So unstressed material will have lattice spacing d naught, and under tension it will under tension or compression it will change to dn. So the lattice will be distorted and your line spacing will be separated, and that will result in change in your that will result in change in your X-ray curves, X-ray peaks. So calculating macro stress for micro strain. So by measuring the difference between the stressed and unstressed spacing, we can calculate the micro strain, and using Hooke's law, then we can then translate this directly into quantitative residual stress. So gamma y is your engineering stress, E and mu E is your Young's modulus, and mu is your Poisson's ratio. Then dn minus d naught by d naught you are calculating from experiment, and this is given as epsilon z, so which is your atomic level strain. So this you have calculated from the shifting of your XRD peaks, and from this you can calculate the stress in your material. So in a single measurement, we got the we got the structure of the material, we got the phase ratio of the mix of different phases, and we also calculated the residual stress. Now we come to how X-ray diffractometer looks like. So this you can see here. This is an actual instrument from the company Bruker. So it's a Bruker powder X-ray diffractometer. So so it describe so modern XRD requires intense radiation. So so the radiation coming from X-rays are very high. So it requires the systems to be fully enclosed in shielded safety cabinets. So as you can see here, they are completely shielded. So inside is a very highly calibrated system, and this is a shield which are panels which are covered with lead lining. So lead blocks the radiation. We studied about lead radiation. Lead has a very high mass absorption coefficient, so it absorbs a lot of radiation, and hence lead lining is used in your shielding to prevent the radiation from coming out and harming you. So the anatomy of a detector. So this is a detector. It is also called a goniometer. So here is your X-ray source. So here your in this region it generates your X-rays, and which are then shot out at your sample. So this is your specimen stage where you keep your sample at the exact center. The X-ray shoots into at the exact center, and the reflected beam is then measured here, which is your detector, which captures the diffracted signal, converts it into your then electrical signal, and then this is a goniometer, which is which keeps your source and detector at fixed angular directions, so that your theta to theta configuration is maintained. On the para-focusing angle, the system utilizes Brentano geometry. So for the diffractor, it is to properly focus into the detector. The source detector in the specimen must always intersect a precise geometrical arc. So this is your goniometric circle, and this is your focusing circle. So your source detector so must always fall on the goniometer circle, which is with your specimen at the center. So as the scanning angle, that is 2 theta, changes, the focusing circle shrinks or expands. So the specimen must remain perfectly centered to preserve this dynamic geometry. So your specimen must always be inside your focusing circle. So it's best to keep it at this at the centered position of your goniometer circle. So photon generator is done in the X-ray tube, so which has your target anode, which is an interchangeable metallic target, typically copper or chromium, which generates specific X-ray wavelengths based on the material, which material you want to analyze. And then you have beryllium windows. So beryllium is very light, so it has very small mass absorption coefficient, so it is highly transparent to X-rays. So it allows the generated photons to exit the shielded liquid cooled tube. So this tube is liquid cooled to keep the temperatures low. So what happens is that the beam that is exiting the beryllium window is scattered in all directions. So it needs a optical manipulation to become collimated. So you have your raw source. So it has multiple beams which are scattered in all directions. So without intervention, the raw beam contains unwanted wavelengths that is k beta, and also diverges widely. So you use physical slits which collimate the physical spread, and then use your filters to filter out the secondary wavelengths, so that only a very clean K alpha beam is reaching your sample. Now your stage is a 360-degree statistical stage. So in a powder sample like alpha silicon oxide, so millions of microscopic crystals sit at random orientations. So you, so your X-rays will give your output for all the orientations. But if you have a single crystal, if you have a single crystal, only some particular orientations are available. So your X-ray will have only some peaks, not all of the peaks. So by physically rotating and tilting the sample through all three axes during the scan, the machine guarantees that every possible crystal plane is eventually exposed to the beam. This ensures a statistically complete diffraction pattern. So it can move in XY, it can tilt, and it can also rotate in 360 directions, so that your every possible orientation comes within your diffraction pattern, so that you can get the complete picture of its crystal. So then then the output is fed into a software, and you get a diffractogram like this, and then the software can calculate the background and subtract the background noise, and then it can identify the peaks, and then it can also and map the position and intensity of the peaks to to known standard data, which is so it can cross reference against the JCPDS database. So JCPDS is a company which maintains a database of structured data of all the different materials, and it can then, by cross referencing your measured output to the standard, you can exactly get which crystal system your material is having, and you can also identify your material through this basis. If it's an unknown material, so the physical constraint of parafocusing, so the Brentano geometry is incredibly precise, but it comes with a strict physical toll. The specimen must fit entirely within the center of the goniometer circle. So, so, so it can only you can only use small samples and not extremely large samples. So, how do you measure the structural integrity for large manufactured components that cannot be cut down to fit inside the box? For that, we use an unrestricted measurement system. So it is built for industrial purposes, industrial related materials which cannot fit into your typical XRD setup. So instead of forcing the sample into a small enclosed goniometer, this system uses an extended open air multi-axis arm to bring the X-ray optics directly to the component. So it has an open arm, so so it can you can place your sample here, and then your arm moves all around the sample in the proper orientations to give you a diffractogram. And to bypass the need of focusing circle, the system abandons divergent beams entirely. It fires a parallel beam directly at the sample with twin detectors that capture the direct backscattered radiation without any spatial reduction. So it has two side-by-side detectors which measure the which sit very next to your beam source. So, so your parallel beam source goes and the direct backscattered radiation is measured. So the angle is provided by your orientation and not your source and detector geometry. So this is called residual stress geometry. So your powder XRD uses Bragg-Brentano geometry with parafocusing circles, and your residual stress XRD uses direct collection. So powder XRD uses divergent beam, which is collimated using a slit, but residual stress XRD only uses parallel beams. Powder XRD has single detector on goniometer arc, so it has and residual set XRD has dual side by side detectors which are slightly off circle. Powder XRD is limit the specimen is limited by the state center, and a residual set XRD the specimen is unrestricted because it is made particularly for industrial components. So your divergent geometry it is used for identification of microscopic crystal phases, and your polarimetry is used for diagnosis of macroscopic mechanical stress. So now we come to some practice questions. X-ray diffraction cannot be applied to study texture in the material, the magnetic structure, the nano regime crystal size, microstrain in the material, dislocation density. So GIXRD is actually called grazing incidence XRD. So what happens is that, let's say, so it is inside, it is a function of your powder XRD. So what happens it at, so at for in typical XRD, you're measuring your material as well as the substrate. Now, let's say if you don't want to measure your substrate, you only want to measure your material. So, what you will have to do is you will have to, on your material, you will have to force light at a very slanted angle, so that your light does not, fall on your light only falls on your light does not so your X-ray beam do not have, are very slanted, so don't go much deeper because they are slanted, so they go like this instead of like this, so they don't go deep into your substrate, so your peaks from the substrate do not come. But what happens for in that is, like, if your my detector is sitting source is sitting here and detector is sitting here, a lot of undifracted light will also enter the detector because of they are almost in front of each other. So for that we use a special type of sample, a specimen stage, which slants your specimen like in the way such that you can measure your XRD at a very slanted angle, and that is called a grazing incidence angle. So it's grazing incidence because it's almost 0 degrees incidence. So you're measuring your XRD at all like 0 to 5 degrees angle, or 0 to 1 degree, 0 to 2 degree angle. That is called a GXRD, grazing incidence XRD. X-ray diffraction cannot be applied to study texture in the material, magnetic structure, nano regime crystal size, microstrain in the material, dislocation density. So the correct answer to this is magnetic structure. So we just studied that we can use X-ray to determine the texture in the material. We can look at the nano region crystallite size. We can also study the microstrain in the sample, and we can also study dislocation density, which is which can be done using phase analysis. The peaks indexed in the diffraction patterns are 110, 200, 211, 220. The index phase represents dash crystal structure, BCC, FCC, hexagonal. So the correct answer here is BCC. So these are the allowed and forbidden pattern. These are the selection rules for different unit cells. So if for primitive, that is simple cubic, all HKL values are aligned, so there are no restrictions. For VCC body centered cubic, your H plus K plus L should be even, and if your H plus K plus L is odd, then it is forbidden. So you can see here, in all these cases, the H plus K plus L is even. Now, if you have FCC, that is face centered cubic, then the allowed reflections should have H plus HKL all odd or all even. If they are mixed, then that is forbidden. So you can see here in 110 it is both odd and even. So this will be forbidden for FCC. For FCC diamond lattice, if HKL are odd, they are allowed. All odd, they are allowed. And if they're all even, and if H plus K plus L is a multiple of 4, then it is allowed. But if H plus K plus, sorry, not H plus K plus L, HKL combined are all even, and their sum is not 4 equal as a multiple of 4, then it is forbidden. And if they are mixed, then also it is forbidden. So again, since we have mixed, so its diamond lattice is forbidden. Now in hexagonal closed pack lattice, if L is even, then all HK values are allowed. But if L is odd, then only those values are allowed where H plus 2k is not a multiple of 3. If H plus 2k is a multiple of 3 and L is odd, then it is forbidden. So you can see here, so here it will be BCC. The material for which you want to quantify the phase fraction is alumina and silica. When you mix a foreign substance like MgO, the method of quantification is called external sample method, internal sample method, direct comparison method. So the answer to this is internal sample method. We just studied about it. In external sample method, you use a pure phase sample of the same material, and you refer between the two different peaks, two different measurements. In direct comparison method, you will directly compare between alumina and silica. That will be called direct comparison method. Among the following options, choose which of the ratio of h square plus k square plus l square for diamond cubic structure. 1, 2, 3, 4, 5, 6, 8, 1, 3, 4, 5, 8, 3, 4, 6, 11, 12, 3, 8, 11, 16. So that is correct. So it will be 3, 8, 11, 16. So we just studied the selection rule for diamond cubic lattice. So let's say 1, 1, 1. So so it cannot have mixed mixed value. So the first possible value will be 111, and so 111 is all odd, so it will be accepted. So 1 square plus 2 square plus 1 square plus 1 square plus 1 square will be 3. So 3 is accepted. The next value would be let's next value will be 222. So 222 is sorry, next value will be 220, and 220 if you see is accepted because because it is, although all are even, so if you measure, so but if you take the sum, it will be, it is 4. 2 plus 2 plus 0 is 4, so it is accepted. And then 2 square plus 2 square plus 0 square is 8, so next value will be 8. Then next would be 113, which comes out to be 1 square plus 1 square plus 3 square 11. Then next to accepted value, so 222 is not, so next will be 222, but 2 plus 2 plus 2 is 6, which is forbidden. So 222 will not be possible. So next value will be 400, which again is possible. So 4 square plus 0 square plus 0 square is 16. So 16, next value 16 comes. So it's 3, 8, 11, 16. Statement A. Residual strain is measured from XRD and stress is calculated from the measured strain. Statement B. Residual stress analysis is based on the de-spacing variation caused in the material during deformation. A is true, B is false. A is false, B is true. Both are true, both are false. That is correct. Both are true. So this we just studied that de-spacing variation is caused due to deformation, and that gives us changes in the peak positions, which is used to measure the residual strain, and ultimately from strain we measure the stress. So both are true. State true or false. The broadening of the XRD peaks is due to slight crystal imperfection. True or false? So it is true, because if your crystal is imperfect, then it will have variable d-spacing, and for the same orientation there will be multiple d-spacings at different so that will result in a broadened peak. The X-ray diffraction curves shows sharp peaks for a crystalline structure because the arrangement of atoms produces destructive interference at angles except for Bragg angle. True or false? So again, this is true. So if you have a highly crystalline structure, then at any angle except the Bragg angle, all the all the scattered waves will combine to get destructively interfered. The intensity of the X-ray diffraction peak at a particular phase is directly proportional to the concentration of that phase. True or false? So this is again true. So we all studied the relation of this. I I alpha is equal to k into C alpha by mu m. So the concentration and intensity are directly proportional. For a perfect defect-free single crystal, the XRD peak shows profile shows very sharp peaks, diffuse peaks, peaks having some peak width, peaks with irregular shape. That is correct. The answer would be A, very sharp peaks. So that we have already studied. What is the breadth B in degrees of XRD peak due to the small crystal effect alone of a crystalline material having a crystallized size of 1000 angstrom? Assume theta equals to 45 degree and lambda equals to 1.5 angstrom. So the answer will be, so use the formula B equals to zero point 0.9 lambda by T cos theta. So lambda is 1.5 and T is 1000 and then theta is 45. So the B will come out as 0.0019 radians, and but we are asked in degrees, so we convert to degrees, which comes out with 0.11 degrees. What strain is required to cause the same peak broadening as the previous question? Assuming theta is 45 degrees, lambda is 1.5 angstrom, and crystallite size is 2000 angstrom. Hint, the Williamson Hall equation you have to use is B equals to 0.9 lambda by T cos theta plus 4 epsilon sin theta. Option A is 0.25, 0.1, 0.02, 0.002. So the answer to this will be C, 0.02. So, so you have to use the same value as before. So that will be 0.0019 radian. So remember the in the equation B is in radians, not in degrees. So if you use 0.11, it will be wrong. So you have to use the radian value, which is 0.019, and then you put the rest of the values, and this solution will come out to be around 0.019, which is 0.02. If size broadening is the only contribution to the peak width, what will be the Williamson Hall plot look like? Linear line, vertical line, horizontal line, or linear line having zero intercept on the y-axis? That is correct. The answer will be C, horizontal line. So, so the B cos theta will be a constant, so it will only result in a horizontal line if there is no strain component. The examination of X-ray diffraction data for magnetic steel shows two phases: alpha ferrite, which is BCC, and gamma austenite, which is FCC. The integrated intensities of the 110 ferrite line is 25, and the 111 austenite line is 3, both in arbitrary units. Calculate the volume percent of retained austenite in steel. You are given R alpha by R gamma equals to 1.5, 10%, 15%, 20%, 25%. So the for the values 25 and 3, the answer should come around 15%. For some reason here, they have used 25, 24 and 4, but for that will result C alpha by C gamma equals to 4. So 4C gamma plus, so that should give your C gamma equals to 1 by 5, which is 20%. But for 25 and 3, you will get around 15.2%. So roughly 15% you will get. Which of the following sum of h square plus k square plus l square integers is not possible for any set of HKL planes? 4, 5, 7, 11. So that is correct. The answer would be C7. So 7, 15, 23, 28. These are not, these are impossible values. So since HKL has to be integer, so h square plus k square plus l square for integers will never be equal to 7. So that are all the questions I had for today. Thank you. If you have any doubts, you can ask, or if you want, you can leave the chat.